Can you hear me?
Yep.
Yes.
And you can see my slides?
Yep.
Yes.
Okay, so it's Wednesday, April 21st, and we're still talking about the structure of globular proteins. And we're analyzing that structure using, well, I'm showing you experimental data, and then I'm also showing you a variety of computational techniques. I mentioned cores of proteins during the last lecture, and I'm going to go into more detail into the cores of proteins in this lecture. So let me click ahead to where we were. Another comment is there were several good questions just on Monday. I appreciate that. That's great. And there was a question about the shape of the distributions of the bond lengths and bond angles. So I wanted to show you that today. The data that I showed here didn't have many bond lengths and bond angles. And so here's an example of a bond angle between three covalently bonded atoms along the backbone. So a nitrogen, a C alpha, and then a carboxyl carbon. And here are examples of that for thousands, taken from thousands of experimentally determined structures, X-ray crystal structures. And so you see, it's not exactly Gaussian, but the deviations aren't that strong. And here's an example of a bond length between a nitrogen and a C alpha. And again, so you see that the standard deviation for the lengths is around a tenth of an angstrom. This is an angstrom scale. And then here it's plus or minus 5 degrees. And so this is, again, just emphasizing that there are degrees of freedom in proteins that are fairly well fixed, determined by the nature of bonded atoms. And then there are other degrees of freedom that aren't as fixed. They fluctuate from one amino acid to another, and from one protein structure to another. And those are the degrees of freedom that are interesting to predict, and that we're going to talk about in this lecture and the next one. So let me click through to where we were. So we had talked about other degrees of freedom that fluctuate more from one amino acid to another, and from one protein structure to another is a dihedral angle. And so every 4 bonded atoms along a chain, you'll have a dihedral angle. If the dihedral angle involves any backbone atoms, so C alpha, so the nitrogen, the oxygen, the C alpha, and the carboxyl carbon, then it is a backbone dihedral angle. And then if it involves exclusively side chain atoms, say C beta and further from the C alpha, then that's called a side chain dihedral angle. And so this is where we were last time. I started talking about backbone dihedral angles. And so the way to, there's a preferred definition of backbone dihedral angles. And so there's phi and psi. So in general, as you move along the backbone chain, there are 4 dihedral angles that you can define. And the way that the chain is broken up is typically through what's called a dipeptide. And so that's basically a central amino acid, and then flanked by half of a amino acid on the left and half of amino acid on the right. And so here I show you an alanine dipeptide, so that it has, that C beta there, as a side chain flanked by 3 hydrogens. The side chains doesn't matter since we're focusing on the backbone, but here's the standard definition for how you define the backbone dihedral angles. So when you're looking at this dipeptide, there are 4 backbone dihedral angles that you can make. There's the, and I'm going to go back and forth because it happens in the literature that C prime means the carboxyl carbon, but sometimes I drop the prime and it'll just say C. So sorry. So if you see C without an alpha or C with a prime, that means the carboxyl carbon. And then if you see a C alpha, then obviously that's the C alpha. And so when you're looking at this dipeptide, if you include the C prime to the left, so that's this one here, and then the N, so you're moving to the right, then the C alpha, and then the next carboxyl carbon, then that's defined as the phi dihedral angle. And so this one includes 2 carboxyl atoms, carboxyl carbon atoms, one from the I-1 amino acid and one from the ith amino acid. So typically the nomenclatures, if you're talking about the central ith amino acid, you drop the I notation. And so then if you just shift shift from the carboxyl carbon to the nitrogen, then you have N, C alpha, the carboxyl carbon, and then the next nitrogen from the I+1 amino acid. And so that dihedral angle involves 2 nitrogens, not 2 carboxyl carbons. And those are the ubiquitous or the frequently discussed phi and psi backbone dihedral angles. And then there are 2 other angles that you can define for 4 atoms along this dipeptide. And they involve 2 alpha carbons. So you can have the I-1 alpha carbon and the ith alpha carbon, or you can have the alpha carbon and the I+1 alpha carbon. And so those 2 backbone dihedral angles are typically very flat. They're either in the 0 or 180 conformation, very flat. And so that's why we're not going to talk about those much, because they don't vary significantly. Whereas phi and psi can have significant variations, and trying to predict what their values are is a general topic of protein structure prediction. And it influences the type of secondary structure that a region of a protein will take on. Going through these slides, I'll try to always have colors that correspond to the particular atom types. So the pink is carbon, the blue is nitrogen, the darker pink. So I'm colorblind, so I'm sort of making these up. Darker pink is oxygen, the whitish is hydrogen, and the yellowish is sulfur. And so sulfurs are rare. They occur in side chains of, for example, methionine amino acids. And so with that definition, you can talk about what are called Ramachandran plots. So Ramachandran was a physical chemist or a chemical physicist in the 60s and 70s, was when he was getting a lot of his work done. And he had the suggestion, and so that's about the time when the first crystal structures, protein crystal structures were being generated. And so there's this idea, we're getting nice experimental information about proteins. Are there any theoretical ways that I can, try to predict that structure or understand that structure? And so he had the idea that I want to try to understand the particular values that phi and psi take on by just considering a single dipeptide. So not trying to predict the phis and psis of the entire structure or in the context of the full protein, but just trying to predict phi and psi based on local geometry, just of a dipeptide isolated from its environment. And so the other thing to think about is, so in general, what a Ramachandran plot is, the backbone dihedral angle phi is on the horizontal axis, and the psi backbone dihedral angle is on the vertical axis. And typically the range that's plotted is typically from negative 180 degrees to 180 degrees. And that's fairly common convention for backbone dihedral angles, but then when you talk about sidechain dihedral angles, they typically go from 0 to 360. So you always have to have an interval from 0 to 2 pi, some interval of 2 pi, but there are different conventions about the beginning and end of that interval. So in general, a Ramachandran plot is a two-dimensional way of plotting the values that are found in proteins. But what's a little confusing is one is a prediction. So Ramachandran generated a prediction, and it doesn't have any experimental data. And another is experimental data, just saying, well, I'm going to look at protein crystal structures and I'm going to ask what I find for the various amino acids. Another thing is that you could imagine Ramachandran plots for different types of amino acids, even though the values you're plotting are phis and psis, which just depend on the backbone, and every amino acid has backbone phis and psis. And so you can talk about a Ramachandran plot for alanine, and you can talk about a Ramachandran plot for leucine, but one of the interesting questions would be, are they similar? That they're not that dependent, they're not too dependent on the side chain. So again, what Ramachandran did with the theoretical model is just considered a dipeptide in the absence of the environment of the rest of the protein, whereas if you're plotting actual data from experimental crystal structures, obviously that particular protein has an environment, and so you're not plotting just the dipeptides in isolation. So since glycine is has such a special side chain, it's different. It has a different prediction than all the other amino acids, which have beta carbons, involved in the side chains. And so that's why we're making a distinction here between non-glycine amino acids and glycine. But the basic idea is he built a sort of physical model for a dipeptide. He basically said, well, I'm going to have the correct backbone atoms of a dipeptide bonded together. I'm going to specify their separations by, the typical values of the bond lengths. And then I'm going to ascribe to those atoms certain sizes. For example, those determined by van der Waals equation of states. So I'm just going to say, I'm going to give each atom a diameter. I'm going to say they're bonded to each other. And then what I'm going to do is I'm going to, imagine physically rotating that dipeptide so it has particular values of phi and psi. So for example, in the plot, you can see that there's a phi. You can ask, well, I have a phi of -90. I have a psi of -90. I'm going to put that dipeptide into that particular backbone conformation. And I'm going to ask, do any of the non-bonded atoms in that dipeptide overlap? So for example, the oxygen of the oxygen of the central carboxyl group, does it have any clashes with the nitrogen? or does the beta carbon of the the side chain overlap with any other atoms in the dipeptide? And so going through that model, what he found was that there were allowed configurations and disallowed configurations based on atomic overlap. So if there were any atomic overlaps, non-bonded atomic overlaps, he said that was disallowed. And if there were no non-bonded overlaps between atoms, that was allowed. And so the exterior region that's white, so for example, I'll pick one, 90° phi and -90° psi, that's in the white region. So that's that's on a disallowed configuration. So all the white region is disallowed. Another one is -90° phi and -90° psi. That's in the exterior white region. And so that's disallowed. But then there were regions that were bounded by sort of the interior regions that are bounded by these black segments. And those were allowed. There were no atomic overlaps at those particular phi's and psi's. So for example, I'll pick one, -90° phi and a 0° or let's say a 45° psi. That's in this, within this interior bounded region. And so that was an allowed configuration. And then he said, well, maybe it's very difficult to know exactly what the atomic diameters are. So I'm going to allow some fluctuations in the sizes of the atoms. And so he said the gray black regions were larger atom sizes, and the larger bounded regions were smaller atomic sizes. And so that was the Ramachandran prediction. And so I just redraw it here. Again, the dashed lines are the small atomic sizes, and the red regions are the large atomic sizes. And then the speckles are alanine dipeptides that are extracted from high resolution protein crystal structures. And so you say this shows to a large degree the alanines in protein crystal structures that are experimentally determined obey the Ramachandran bounds. And so even to this day, the quality of a protein crystal structure can be evaluated by how many what are called Ramachandran outliers there are. And those are specks, or these little dots, or instances of amino acid backbone dihedral angles that don't fall in the Ramachandran bounds. So one thing that's hard is the more refined details of this map. So for example, in later studies in the community, as well as my studies, have found that the particular conformations that phi and psi take on can be influenced by other things, like the tau angle, which is a particular bond angle of the central C alpha atoms. So for example, tau is the bond angle between the nitrogen, the C alpha, and the carboxyl carbon. And so if that angle is larger, then you can get a wider range of allowed conformations versus when it's smaller. And so that has shown to be influence which phi's and psi's can occur. Another subtlety or importance is the density of points. So for example, the points in this plot are not uniformly distributed. So in this particular plot, there's a lot of points in the lower region, which tends to be more alpha helical structures. And so then the question is, what causes that? Should protein force fields include that there's sort of a bias towards alpha helical structure, or do I just uniformly sample the allowed conformations from the Ramachandran plot? So should I sample alpha helical conformations more, which are those with lower values of psi, or should I uniformly sample the entire allowed Ramachandran space? So that question has been discussed a lot, both in the community and by my group. And so I reproduce, in the upper right corner, so panel E, is data of alanine dipeptides from high resolution protein crystal structures. And so you see here, I actually plot a probability density where the color determines the probability of having a particular phi and psi. So for example, yellow is relatively low probability, whereas red and black is much higher probability. And so then this strong peak at alpha helical values shows up. And so again, I say again that the question is, when I carry out a simulation, do I include this bias in my force field, or was that bias created by the data set that for some reason experimentalists chose alpha helical proteins to crystallize, or alpha helical proteins are easier to crystallize? And so there's another database, and what they try to do is basically try to create a more disordered database of protein crystal structures. Unfortunately, to some degree, it turns out that you basically just remove alpha helices. So if you remove this more disordered database of alanine dipeptides, looks like you basically remove the alpha helical content and then peak in the more beta sheet-like content shows up. And so then the question is, well, is this a more sort of intrinsic phi psi distribution that's not affected by which proteins crystallize, or that experimentalists choose alpha helical proteins over non-alpha helical proteins? So then in the other panels, so that's sort of still a lingering debate about what is the intrinsic phi psi distribution for a single dipeptide. So another approach you can take is look at, and we'll talk a lot more about molecular dynamics, but just for now, assume that there are simulations exist where they can carry out molecular dynamics of proteins, but also just single amino acid dipeptides in water. And then you can just try to measure through molecular dynamics simulations, try to measure the intrinsic phi psi probability distribution of an alanine dipeptide. And so I show basically very common force fields. There's a couple amber force fields in A and B. So A and B, so the left column is an amber force field, and then the other is a charm force field. So those are sort of the two monolithic, or the two big players in the force field, molecular dynamics force field community for proteins. And so what I want to show here is one thing is that sometimes the force field doesn't work that well. So for example, in C, you see that you get psi values around relatively abundant psi values around -120, which is not really borne out in the crystal structures, although some of the coil databases do have some -120 values. But again, there's also not, and also you can get different values of sort of the middle section. So for example, in panel C, for this particular charm force field, there's not a lot of values at psi equals 0 degrees, whereas in some of the other force fields there are. And then again, they also don't agree on the relative beta and alpha helical content. So in general, I would say that currently there's still some debate about the intrinsic propensities for forming alpha helical and beta sheet content. And I will address that in these discussions by sort of advocating for a simpler approach, not using the current atomic force fields. And again, I'm happy to field questions if I didn't spend enough time on a particular topic. So what I discussed currently was backbone dihedral angles. And I basically said that that's a degree of freedom that would be very valuable to predict. You can see here, and you can see in the experimental data for the Ramachandran plots, the values of phi and psi span a wide range. There's a wide range of angle values that they can take on. And so you can't just set it, in your computational model. You have to somehow, you have to be able to predict what it will be. But I did say that there is a simple, the Ramachandran idea of preventing atomic overlap is a good idea. It at least lets you bound it. And we're going to try to take that further with sidechain dihedral angles. So we're going to focus on side chains or amino acids that have side chains that tend to appear in the dense central regions of the protein, which are cores. And so that's going to be isoleucine, phenylalanine, valine, tyrosine, tryptophan, leucine, threonine, and serine. And so these have abundances in the central regions of proteins. And they have different side chains, and I think almost all of them have two. So threonine and serine have one dihedral angle. The others have two dihedral angles. And those dihedral angles are going to be called chis. So the lower value of chi is closer to the backbone. And then as you go up, chi1, chi2, chi3, you move further from the C alpha atom. And so a hallmark of side chain dihedral angle distribution, so this is for threonine, where you just have one side chain dihedral angle, is they're called rotameric. So rotamer means you can, you're going to rotate through the side chain dihedral angle possibilities, but there are typically 3 possible values. And that's what, so this is the distribution of, probability distribution of threonine side chain dihedral angles in high resolution protein crystal structures. And you typically get 3 values. So I'm just focusing on like the central regions of this like 3 peak distribution. So there's one at 60 degrees, a peak at 60 degrees. There's a peak at 180 degrees, and there's a peak at 300 degrees. And there's a peak, and then there's some distribution around that peak. But you don't typically find dihedral angles at 120 degrees or 240 degrees. And so that's what I mean by rotameric. It's not a flat distribution. It's a highly peaked distribution. And then one of the interesting questions, I mean, the full question is, can I have some theoretical or computational model that would predict this distribution exactly? But a simpler question is, well, can I predict the relative heights of these peaks? So the 60-degree and 300-degree values are roughly equiprobable, whereas the 180-degree peak is less probable. And so you're more likely going to see 60 and 300. Is there some way to understand that? And then you can say the same thing. You can ask the same types of questions for other side chains of these amino acids. So isoleucine it's a little bit longer or bigger. So it has 2 side chain dihedral angles, chi1 and chi2. So in general, there should be 9 rotamers, or in principle, there could be 9 rotamers because you have 3 for each side chain dihedral angle. So you have 3 times 3. And so in principle, there could be peaks in the centers of each of these 9 bins. Because in general, we say that side chains are rotameric. But what you find in the experimental structures is that they're not equiprobable. So you don't get 1/9 in each of these bins. You get, a whopping 60% in the rotamer bin number 6, which corresponds to a chi1 of 300 degrees and a chi2 of 180 degrees. And then you get some pretty good probability in 3 and 4 as well. And so again, an interesting question, and one that's basically sort of step 1 in protein structure prediction is, can I predict this highly non-uniform probability distribution? And the specific question that I ask in my group, and that I'm going to talk about in the next set of slides, are the following 3 questions. Can the structural properties of protein cores be quantitatively modeled using the approach that was adopted by Ramachandran? That I'm going to ascribe sizes to each of the atoms along the backbone and along the side chain. I'm going to obey the bond lengths and obey the bond angles. And then can I predict features of these side chain dihedral angle distributions? If I do ascribe sizes to these atoms, and I am able to predict the side chain dihedral angle distributions, then those sizes mean something. They have utility, they're useful. And so then I can ask, well, what's the packing fraction? Because if atoms have sizes, you can treat them as physical objects with size. And then I can ask about the packing fraction. And then my group has been using the packing fraction basically as a feature for protein structure prediction. So let's take a 1 to 2 minute break while I just call up the next slide presentation. 30-second break. So can everybody see this? Maybe I get 1 thumbs up. Got it, thanks. Okay, so just at the, since this work has appeared in research papers, I just want to thank my collaborators. So Lynn Regan, who used to be at Yale in molecular biophysics and biochemistry, I talk to still to this day once a week. And so she's played a big role in this. And then these are 4 former graduate students that did a lot of this work. And they span physics, engineering, and computational biology. So I just include these papers in the notes so that if you want to read more on these topics, you can. So these are some of the papers that have come out on these topics about core packing, core repacking, things like that. So I, again, repeat these questions. Constructional properties of protein cores, and I'm specifically talking about the side chain dihedral angle distributions of core residues. So if you have a core residue, do you know exactly where the side chain is? Can it be quantitatively modeled using just a very simple force field? And that force field is just going to be whether the atoms overlap or not. If it can, if you can just say, well, I can predict protein structure by knowing whether atoms overlap or not, then they do have a physical size, and you can ask, well, what is the packing fraction of a core? And how does it compare to other materials that we see in, say, physical systems? And then hopefully I'll get to a little bit about you know, computational design and computational approaches for protein structure prediction. But let me just say one thing at the outset is that these slides are going to focus on protein cores, and so I just want to remind you why I think that's interesting. So one is that protein cores are known to determine the stability of a protein. So for protein, a core is more densely packed or it's more cohesive, then the melting temperature of that protein is known to be higher. So, you know, if you study protein cores, then you're intrinsically studying the stability of a protein. Another thing which I've alluded to is I've said that there is a suggestion from our work that the core can act as a template of the three-dimensional fold of a globular protein, so that if you do understand the core, so for example, if you can predict the size of the core, which residues are in the core, then you may be able to do a really good job of folding a protein, because it's templated in the sense that the core structure determines some of the less core and surface structure of a fold. And then another area is that when two proteins bind, you know, for example, the surface of protein A and the surface of protein B bind together to form a complex, the two surfaces are then buried. And so it's well known that that buried interface acts for all intents and purposes as a core. And so the question is, can we apply all the results that we found for individual protein cores to the binding of proteins themselves? And so those are three motivations for focusing, and then one more will be mutations, and I hope I get to that. Okay, so onward and upward. So I think this took off in the 90s, is this idea of validating computational protein structure prediction software from this particular question or problem, and it's called the protein repacking problem. And I'll first explain it just with a cartoon, and then I'll explain it in detail. So the cartoon is, you take a jigsaw puzzle, say, let's just consider a 2D jigsaw puzzle, so one you construct on a table or flat surface, and you put it all together, and then you take out the, let's say there'll be 5 or 10 pieces in the central region of that jigsaw puzzle, and take them out. So just remove them and put them aside and mix them up. And so the question is, you have this missing central region of the jigsaw puzzle. Is there only one way to put the jigsaw pieces back together and solve the jigsaw puzzle with the remaining pieces? And the idea of a jigsaw puzzle, which makes it solvable, uniquely solvable, is that there's only one way to put a jigsaw a puzzle together. And so the jigsaw repacking problem of putting the central jigsaw puzzle pieces in the central region is a unique exercise and can be done. And the question is, and the reason why that is because the jigsaw puzzle is so densely packed and the puzzle pieces are so unique or so determined. They're not spheres, or they have these unique shapes, and the ways in which the puzzle pieces fit together is very unique. Whereas if the jigsaw puzzle was not as dense, it was more dilute, the puzzle pieces didn't exactly fit together, then there would be many ways in which the jigsaw puzzle could be put together. And so people started asking that question in the 90s of that protein repacking puzzle, where you take an experimentally determined X-ray crystal structure, a protein, and you look at the amino acids that form the core, and you take them out. And so you can imagine various levels of difficulty of this exercise. You could take the entire amino acid out. You could also take the entire amino acid out and like rotate the relative dihedral angles to to sort of mix it up so the amino acids don't have their original shapes. And you could also sort of mix up the identities that you didn't know. You could sort of try all identities of the puzzle pieces. Is it a threonine, a serine, and so on and so forth. So I'm going to ask a sub-problem where I'm going to keep all the identities the same. So I'm going to say I'm going to take out 6 residues from the core, but I'm going to remember which ones I took out. I'm taking out a methionine, an isoleucine, a cysteine. I remember taking those out, and I'm going to keep those identities fixed. The other thing I'm going to do for the time being is I'm going to keep the backbones there. So I'm not going to take out the amino acids themselves. I'm just going to take out the side chains. And so that's a much easier problem. Now I know what the amino acids are, and I know which side chains correspond to those amino acids. I just don't know in what conformation I'm supposed to put the side chains back on. Do I put them on in an extended way? Are they bent in certain ways? What conformations of the side chains do I put back on? And so that's called the protein repack. It's called the protein side chain repacking problem. And it's a way to validate your force field. If you're able to put them back in the exact way that the crystal structure has, then it's thought that you then have a pretty good force field. But in the beginning, it wasn't clear whether you could do it, because if there's a lot of free space, so the way that I'm going to do it is I'm not going to rely on a very complicated force field. I'm going to just put them back with using atomic overlaps. Whereas other people will try to put them back on using a complicated force field, which doesn't just include atomic overlaps. It includes it can include electrostatics. It can include hydrogen bonding, and so on and so forth. So any questions about protein side chain repacking? Or any other topics I talked about so far? Okay, I'll keep going. So I love sometimes I love quoting old literature, as long as and then making fun of it, as long as it's not mine. So here I'm going to make fun of. There's this nice. It's not exactly a review paper, but it reviews. Thinking about proteins cores as sort of packed, densely packed objects. There's a lot of work in the 80s. And so then this paper, in the 80s and 90s, and so then this paper came out in early 2001 and sort of said what the current state was. It's done by Ken Dill and Liang. Both of them I've talked to, and I know they're. And so Ken Dill is has done a lot of work in using computational models to fold proteins. But I get to make fun of his early work here. So he there's this paragraph from this paper, and he says, what is a good model for the packing inside a protein, which is one of the questions we're asking here. Is a protein packed more like a liquid or a solid? So in that question, he's asking, if it's packed like a liquid, then each of the liquid atoms or molecules can freely move around. Whereas if it's a solid, then they're locked in place. Based on observations of high packing densities and low compressibilities, so sort of solid-like features, protein cores are often considered to be more like solids than liquids. Packings in proteins was first analyzed quantitatively by Richards. So Richards is a real pioneer in this area, and he worked at Yale in the molecular biophysics and biochemistry department. And Richards used a Voronoi analysis, which I'll talk about in detail in a couple of slides, for proteins in a space-filling model where each atom is taken to be a sphere with a fixed radius given by the van der Waals radius. So these and other classic papers showed that the average packing density inside a protein is as high as that inside crystalline solids. And this yellow shaded region is the region that I want to make fun of, because that's impossible. So when I think of crystalline solids, I think of like metals. Metals are classical crystalline solids. They, the atoms in a metal are arranged in very ordered arrangements, and they're very dense, and their packing fractions are very high, typically in the mid 70% to 80%. So most of space is containing atoms. And so my question that I want to answer today, and I think it has implications for protein structure and computational protein structure prediction, is why can that not be true? And to answer that question, we have to answer these intermediate questions. So what is exactly a hard sphere model for protein structure? How do you choose the atom sizes? Do you need explicit hydrogens? So early on in this field, there was a extended atom model which subsumed the hydrogens into the heavy atoms. And so in this work, we're not going to do that. We're going to have explicit hydrogens. And so that can make a difference. Then I'm going to show you why that yellow statement doesn't make a lot of sense, and that the packing fraction has to be below that for crystalline materials. So I do want to mention that I do say X-ray crystal structures a lot. And so that could be confusing, but when you have an X-ray crystal structure, the proteins, the entire protein sits on some type of crystal lattice, but the individual atoms within a protein do not sit on a crystal lattice. And that's the distinction I'm making. So again, like the center of mass of each protein in a crystal structure can sit on a crystal lattice. But the question that we're asking today is whether the individual atoms in each protein are sitting on a crystal lattice. And those don't have to go hand in hand. So just to remind you, these are the amino acids that I'm talking about. These tend to be the hydrophobic amino acids, as well as serine and threonine, which tend to appear in the cores of proteins. I don't think I've shown this before, but I wanted to, I just wanted to let you know that we do have lots of structures that are high resolution. And so we have a few thousand in typical cases of each type of residue. And so it provides a large data set of the side chain dihedral angles. I've already shown this. The degrees of freedom that we're going to be interested in are the dihedral angles, not the backbone stereochemistry. So again, what we're interested in is understanding what's the connection between atom size and the ability to predict side chain dihedral angle distributions. So I don't think I've shown this one before. This is the Valine side chain dihedral angle distribution from X-ray crystal structures. So Valine just has one side chain dihedral angle, chi1, and in contrast to threonine, the central rotamer, the 180-degree rotamer, is very highly probable, whereas the outer ones, the 60 and 300, are a factor of 3 at least less likely to occur. And again, leucine and isoleucine have two side chain dihedral angles, and so 3 rotamers per side chain dihedral angle. So in principle, there can be 9 rotamers, but leucine tends to have 1 very highly populated rotamer and 2 sort of weakly populated rotamers, and then leucine has 2 more equally probable rotamers of the 9. And so the idea is there a hard sphere plus stereochemical constraint model, basically a Ramachandran type model, that can predict these side chain dihedral angle distributions. So again, taking snippets from the literature and then making fun of it in a very nice way. Here is a snippet from a sidechain repacking paper. I think from the mid 2010s. So it says, in recent work, Peterson and co-workers performed sidechain recovery for 200 proteins using 6 different protein software suites. And so protein sidechain recovery is basically this sidechain repacking that I was talking about. And so they use Squirrel, and each of these each of these software suites has interesting names. There's Squirrel, SCWRL. There's Oscar. There's RASP, SC Comp, Rosetta, and they're going to use these different software suites and compare their performance. The key component of computational protein design software is the energy function, and it includes many terms. So this is the approach of some of a lot of the community, is they'll include a lot of terms in their energy function. So it's stereochemistry, which I agree is very important. So it's potentials that enforce bond lengths and bond angles. And then they include lots of additional terms. Statistical potentials that sort of bias the side chain rotamers, repulsive and attractive van der Waals interactions, hydrogen bonding, electrostatics, disulfide bonds. And the last one I don't like, ad hoc pairwise residue potential. I don't like anything that begins with ad hoc, because that sort of means synonymous with wrong. And then the biggest thing is that we're not sure what the weights for those, you have 8 terms. There's lots of different weighting functions you could add. The second term's really strong, the 8th term's weak, the 8th term's really weak, really strong, the second term's really weak, all sorts of different types of weightings. And so with this type of approach, it's really hard to understand which of the terms is dominant, or if, is it possible that there could only be a couple dominant terms which would actually be able to do sidechain recovery really well. So we take a different approach. There's basically 2 of those terms of the 8 that they talked about. So the one is the stereochemistry. We respect all the stereochemistry I discussed. That is, bond lengths are enforced, all bond angles are enforced. And then the only thing that we add is a non-bonded interaction, which looks like the top equation. So the top equation, if you don't like equations and you want to see a picture, I'll show a picture in the next slide. basically says if two atoms overlap, if two non-bonded atoms overlap, there's a large energy penalty, so the energy increases rapidly. But if two non-bonded atoms don't overlap, then there's no energy cost. So this energy function really weights conformations that don't have atomic overlap. It weights those very highly relative to conformations where there's non-bonded atom overlaps. And what you can do is use a Boltzmann weighting, to favor conformations with little atomic overlap. So here's the movie. So then what we do is you can ask, and I'll emphasize this more in the next slide, is you can do the Ramachandran thing where you take the amino acid out of the context of the protein, and you can include it in the context of the protein. So if you take the amino acid, like I'm showing here, this is a leucine amino acid taken from a protein crystal structure, but then it's just in vacuum. There's nothing around it. And so what you can then do is try all possible combinations of the side chain dihedral angles. And then you can ask, are there intra-residue overlaps? So INTRA. So intra meaning, are there overlaps between non-bonded atoms that exist within this leucine dipeptide? And so that would be like the analogous Ramachandran question about, if I isolate this dipeptide, do I have overlaps at certain specific values of Chi1 and Chi2? And then you could also ask, I'm going to place this leucine in the context of its experimental crystal structure. Then I do rotations and I ask, are there overlaps coming from atoms within the residue as well as atoms in the residue that I'm on, like this leucine, with other residues in the surrounding environment? And those would be inter-residue or inter-amino acid, that's INTER, atomic overlaps. So for this particular movie, I'm just going to look at intra-residue overlaps. And so the vertical axis represents the overlap energy between atoms, non-bonded atoms. And so you're going to see fluctuations that occur. The energy is going to go up and down depending on what Chi2 value I select. And so in this particular map, I'm fixing Chi1 and I'm varying Chi2, but you can imagine that in general, I want to do this in a two-dimensional plane and then map out the surface, the energy as a function of Chi1 and Chi2. And it's not playing. So hold on one second. Okay, so I'm going to have to play that movie tomorrow because I have to locate it. So it's this issue of that the PowerPoint is having trouble locating the original movie. And so I'll just describe it to you and then I'll show it to you during the next lecture. So basically what's going to happen is that as you sweep Chi2 from 0 to 360 degrees, it's going to fluctuate up and down. And what it turns out is that the 180-degree conformation of Chi2 is the lowest energy structure. And so that's where we're going to predict that this particular side chain dihedral angle should be placed. So what I want you to imagine is that I don't know the sizes of the atoms a priori, that there's no there's no sort of Wikipedia page or lookup table where I can just say, oh, well, this is the size, of each atom, because the size of an atom is an intrinsically quantum mechanical phenomenon. And so in that sense, the size of an atom could depend on its conditions. So if it's in a liquid environment, the size of an atom could appear to be a certain size, whereas if it was in a more condensed environment, it would have a different size. So I'm going to treat the atom size currently as a variable, and then within reasonable bounds, and then I'm going to say that I'm going to choose the atom size that does the best side chain recovery. And so then atom size has meaning to me in this context. It is the atom size that yields the proper experimentally determined side chain dihedral angle distributions. So for example, what I've done here is I've looked in the literature. The colorful symbols represent literature values, both experimental and computational values of the atomic radius that have been quoted for the different atoms. And I've also allowed two different values for the carbons. So I have a different size for the carboxyl carbon compared to other types of carbon. And so what we did is we did these sidechain recovery analyses as a function of size over the full range of these colorful symbols, so the literature. So you can imagine randomly sampling combinations of atomic sizes and then seeing how well sidechain recovery goes. So for example, I'm just going to pick one randomly. The hydrogen is 1 angstrom, the nitrogen is 1.5 angstroms, non-carboxyl carbons are 1.8 angstroms, carboxyl carbons are 1.5 angstroms, the oxygens are 1.4 angstroms, and sulfur is 1.8 angstroms. So that's a random choice of atom sizes within this distribution. And so we tried all of them, and all is in quotes. We randomly sampled and tried a lot. And what you find is that the black symbols give the best agreement to sidechain recovery just as with the dipeptide model. Okay, so now we have atomic sizes, and we're going to try to do, we're going to try to see if we look at the amino acids in the context of the protein, does it specify the side chain exactly? I'm going to skip this because I'm going to talk about it later. This is talking about how we decide which residues are core residues. And so this is what I was talking about before, that if you look at a residue in the absence of its, so if you look at a core residue not in the core, you just look at it isolated. So you have the condition on the left that the overlaps between atoms can only arise from within your residue, whereas if you're looking at the leucine in the context of an experimental crystal structure, it can have atomic overlaps with neighboring residues. So then I show you the results from the dipeptide. Is that so? In the example of isoleucine, you see the experimental data is on the left, and again you see that their rotamer number 6 is very highly probable, 60% probability in that particular rotamer. And then you have the prediction from the dipeptide isoleucine, and you see that I get the rotameric features right. So the atom sizes are calibrated in that sense. And you see that you're starting to see a preference for rotamer 6, but the the probabilities are a little too uniform, that the probabilities in 3, 4, 5, and 6 are relatively close, whereas there's a big difference between rotamers 3 and 4 and number 6. And what we believe will happen is that we'll be able to predict the experimental probabilities more exactly if we look in the context of the protein. Okay, and so that's what we do. So here I switch to an isoleucine. Sorry, I look at, yeah. So I'm still looking at an isoleucine. For this particular isoleucine, again, the dipeptide gives a more uniform probability. It doesn't exactly agree with the dipeptide from the previous example because the bond angles and bond lengths are a little bit different for this particular dipeptide, this particular isoleucine. But you again get the rotameric feature. But then when you put this particular isoleucine 56 from this protein 2NWD, that's the protein data bank identifier, then what you do is you look at this isoleucine in that protein environment, and then you try all the Chi1, Chi2s, and then you see that there's only a probability density at location number 5, which is where the crystal structure is. So the X corresponds to the side chain dihedral angle that's in the crystal structure itself. And then we find if we sample all of the possible Chi1 and Chi2s, the only one that doesn't allow intra and inter residue overlaps, large overlaps, is the one that's very close to the one that was observed in the protein crystal structure. And so that's really good news. And it suggests that since it worked for that particular isoleucine 56 and 2NWD, well, why wouldn't it work for other residues? And if it does work for other residues, then you can exactly recapitulate the observed side chain dihedral angle distribution, because that's how the experimental distribution is constructed. So this works for other residues as well. If you look at phenylalanine, the dipeptide prediction looks a little bit different because, well, first of all, it's a Chi1, Chi2 map. It's a little broader, but then when you localize it to the environment so that you allow both intra and inter-residue overlaps, you get that the specific side chain dihedral angle combination that's in that particular crystal structure is the only one that's allowed. And the same thing for valine. When you look at a particular valine, you get a rotameric structure if it's just in the dipeptide model. But then when you put it in the context of protein, then only the particular one that's sampled in the particular crystal structure that we look at, that's the dashed, the dotted vertical line, is the prediction agrees with the one that occurs in the crystal structure. And so then what you can do is, instead of just doing one isoleucine, you can do all the isoleucines in a particular data set. And so I just showed you an example of one, but we did all of them. And then you can basically combine the distribution. So you put one particular isoleucine in the protein environment, you sample all Chi1 and Chi2s, you get your prediction, then you do the next one, you get your prediction for the probability distribution, and then you average those probability distributions over all possible residues. And that's what panel B is. And so when you include the environment of the protein, you get a quantitatively accurate prediction of the side chain dihedral angle distribution, in particular rotamer 6 for isoleucine is very highly populated, around 70%, and 4 and 3 are much lower than that, but they're still non-negligible values, 12% and 7%, and it's very quantitative. So with that, I will end for today since it's 2:15. Next week, I will finish this presentation. I will show you the movies of the hard sphere plus stereochemical constraint model so you can see how I'm doing these side chain dihedral angle rotations. And then looks like I'm running one lecture behind. And so the following lecture on Monday, I will start with intrinsically disordered proteins. So again, we're having an extra lecture this week. So it's Thursday, tomorrow, Thursday at 1, I'll finish up globular proteins. And then on Monday, I'll start intrinsically disordered proteins. I'll pause for a little while for questions, and then we will sign off.